Welcome back. In this lecture, we're going to talk about two topics. The first one is we'll consider Fourier series for functions whose period is not necessarily 2 pi. And we'll call the period 2L for reasons which will become clear later in the course. But it's an analogy to using 2 pi for the original length of the intervals. And then the second topic is if we have a function defined on the interval from 0 to L, then we can do either even or odd extensions to the interval minus L to L, and that will yield a cosine series or sine series depending on whether we do an even extension or an odd extension. And these even and odd extensions, as well as considering general periods, will be useful in applications when we study partial differential equations, starting in a couple lectures. Okay, well, since we're going to develop the theory for 2L periodic functions as a complete analogy to what we did for 2 pi, for a warm-up exercise, do you remember the way we used the inner product and the projection formula to understand Fourier series, in particular truncated Fourier series, as orthogonal projections? So remember, the basis for Fourier series is that if you're considering 2 pi periodic functions, the set 1 cos t, cos 2t, and so on, sine t, sine 2t, and so on, is orthogonal for the inner product which was the integral from minus pi to pi, the inner product of f and g was integral from minus pi to pi of f of t times g of t. And so when we projected onto the span of 1, the first n cosines and the first n sines, we had this projection formula, and that led in the limit to the Fourier series that we wrote as a naught over 2 plus the sum as n goes from 1 to infinity of an cos nt plus the sum as n goes from 1 to infinity of bn sine nt. And the point was that the constant term, a naught over 2, was, we took the first orthogonal function and we dotted it with f, took the inner product with f, then we divided by 1.1, the inner product of 1 with itself, then we multiplied by the function 1. That gave the first term. And then the ANs were just the inner product of f with cosine nt divided by the inner product of cos nt with itself. And so the numerator was just the integral from minus pi to pi of f of t cos nt. The denominator was the integral from minus pi to pi of cos squared the average value of cos squared is a half, because cos squared plus sine squared is 1. And so the answer here was 1/2 times the length of the interval, 2 pi, which was pi, so we got a 1 over pi. And I should have said the a naught over 2 was just the integral, the numerator was the integral from minus pi to pi of f of t dt. And then the average value of the function 1 is 1, and so the integral, the denominator, which is just the integral from minus pi to pi of 1, boy, I made that long, is just 1 over 2 pi. And as I always emphasize, this is just the average value of f. And the only reason we write it is a naught over 2 instead of a naught is then you have the 1 over pi's in front of the integrals for a naught, just like you do for the rest of the a_n's. Okay, and the b_n's were the inner products of f with sine nt over the magnitude of sine nt squared in the inner product sense, which was the inner product of it with itself. Okay, so, and the numerator turned into the integral, the denominator turned into pi, and we got the formulas that we use for the sine coefficients. Okay, so because we all remember projection from linear algebra using the standard dot product, I like to think of this way of motivating Fourier series. We're going to use exactly the same way for 2L periodic functions instead of 2 pi periodic. So here is the Fourier series theorem. First of all, let's think about what the analogous functions are going to be. So they're supposed to be 2L periodic. So 1 works. What's the smallest omega for the cosine function I can take? Well, as t goes from minus L to L, I want the cosine of I want the multiple of t to go from minus pi to pi. So that's why cosine pi over LT is the first function in the list, right? As t goes from minus L to L, pi over LT goes from minus pi to pi. So this will be a 2L periodic function. And then you get all omegas, which are multiples of that. And similarly, you'll have sine pi over LT, sine 2 pi over LT, and so on. So that's the corresponding set of functions, and that's why you see this Fourier series here using those functions. All right, so that set, that rescaled set of functions, of sinusoidal functions, is going to be orthogonal with respect to the right inner product for 2L periodic functions, which is just the inner product of f with g is the integral from minus L to L of f of t times g of t. Okay, and this Fourier series can be understood exactly the same way as we did it for 2 pi periodic. So the definitions of the Fourier coefficients are listed on this page. The a naught over 2 is 1 over 2L instead of 1 over 2 pi times the integral from minus L to L of f. And you'll notice that the integral is just the inner product, this new inner product of f of t times 1. And the 1 over 2L is the integral from minus L to L of 1 squared, which is just 2L. So that's the formula for a naught over 2. For an, the integral in the expression is just the inner product, our new inner product of f with cosine n pi over lt. And the 1 over L is just the integral of cosine squared n pi over lt from minus L to L. And again, the average value of cosine squared is 1/2, so I get 1/2 L. Okay, so this is exactly what we were reviewing in the warm-up exercise, except we're doing the same thing on an interval of length 2L instead of 2 pi. Okay, so let's check that the orthogonality of our new set of sinusoidal functions just follows from the original orthogonality for 2 pi periodic ones. And we'll do it with a change of variables. So in general, if we have functions f and g, which are 2L periodic, let's do a change of variables. So as t goes from minus L to L, pi over LT will go from minus pi to pi. So let's change variables. Let's call tau pi over LT, and so by symmetry, t is L over pi tau. And let's make that change of variables in our integral for the inner product of f with g. So we substitute in the integral, we substitute tau equals pi over LT. So d tau is pi over L dt, or dt is L over pi d tau. All right, and when we change variables in a definite integral, we change the limits at the same time. So as t goes from minus L to L, tau will go from minus pi to pi. In the integrand, I just made the substitution, and then I replace the dt with pi over L, dt with L over pi d tau. And look what we've done. What we've got on the right is L over pi times the inner product for 2 pi periodic functions. And under this change of variables, the one function goes to the one function. The cosine n pi over LT function goes to the cosine n tau function, because tau is just pi over LT. And it's the same for the sine of the n pi over LT functions. They go to the sine of the n tau functions. So since all of the inner products were 0 for the sine n tau, cosine n tau, and 1 functions, as long as we took different ones of those, they were all orthogonal, we get the same result for these rescaled sinusoidal functions. So the orthogonality of the new functions is implied by the orthogonality for the rescaled for the original inner product of the original functions. And it's easy to check, if you want to think about it, that you get the same convergence theorems we had for 2 pi periodic. You get the same integration, differentiation, term by term theorems as we talked about in the last lecture. All right. So I think I might have already mentioned this before, but why would we want to consider 2L periodic functions? It's because of applications. In terms of the mathematics, if you have a 2L periodic function, you can always do a change of variables or units to make it, to consider your problem as if your functions were 2 pi periodic. Okay, so let's illustrate that fact by talking about the following theorem, which can be useful when you've already found 2 pi periodic Fourier series and you have a function which is 2L periodic, which is related to a rescaling or a linear combination of 2 pi periodic ones. And this shows up in your homework. So here's the theorem. Let's start out with a 2 pi periodic function with a known Fourier series. And now consider the rescaling of that. So originally, in this function, in the f, the t's are going from minus pi to pi. And so if we take pi over LT, those t's will be going from minus L to L. Correspondingly. So, look, I didn't say that very well. So, if here the arguments are going from minus pi to pi, then if we want a function where the variables are going from minus L to L to be periodic, we would want to rescale the t variables from minus L to L by multiplying them by pi over LT. All right, so that's what's going on here. So the function f of pi over LT will be periodic with period 2L, and we're assuming f is piecewise continuous with a Fourier series. So this rescaled function, which I'm calling f tilde of t, will be piecewise continuous and periodic with period 2L. And the theorem is, to get its Fourier series, you just replace all of the t's in the 2 pi periodic expansion with pi over L t's to get the Fourier series for the 2L periodic one. And the proof is straightforward. We just compute the Fourier coefficients. So F has a Fourier series, as we talked about on the last page, where we have the formulas for the Fourier coefficients. So for example, A naught tilde over 2 is the average value. It's 1 over 2L, the integral from minus L to L of F tilde of t dt, which is 1 over 2L, the integral from minus L to L of F of pi over L t dt, and we do the same change of variables that we did on the previous page. We're really redoing what we did on the previous page. We write tau is pi over LT, t is L over pi tau, dt is L over pi d tau. This integral will be 1 over 2L. As t goes from minus L to L, tau goes from minus pi to pi. This is f of tau. dt is L over pi d tau. The L's cancel. And you get the formula for A naught over 2, which is 1 over 2 pi times the integral from minus pi to pi of f of tau d tau. Right? The formula for A naught over 2 for the 2 pi periodic function. And let's just check the AN tildes. It's exactly the same. So they are 1 over 2L integral from minus L to L of F tilde of t dt, which is 1 over 2L integral from minus L to L F of pi. Oh, I forgot my cosine NTs. My cosine, not NTs, they are N pi over L T's dt. And this is 1 over 2L integral from minus L to L of F of pi over L t cosine N pi over L t dt, and you do the same change of variables and everything cancels exactly the same way, and you end up with 1 over, oh, there's no 2 in the ANs, just in the A naught over 2. And you end up, well, let's fix it here too. That's here, oh no, that was good there, never mind. And you end up with 1 over pi integral from minus pi to pi of f of tau cosine n tau d tau. Right, so it was tau. It's the same, but the integrands are different, so let's just look at it for a second. Tau was pi over LT, t was L over pi tau, dt was L over pi tau. So what you really had was 1 over L, the limits changed, and multiplying the d tau was the L over pi. Okay, so you got exactly, after you canceled the L's as above, you got the original Fourier cosine coefficient for the 2 pi periodic function. And it's exactly the same for the sine coefficients. So let me illustrate this with our favorite example. Well, I don't know if the tent wave or the square wave is our favorite. So here's a shortcut if you want to get the Fourier series for the period 2 tent wave. So g of t is absolute value of t as t goes from -1 to 1, and then extended as being period 2 periodic. So in this picture, as t, you want to rescale the domain. So t is going from -1 to 1. And to get something going from minus pi to pi, you multiply your t's by pi. Okay, so we know the tent function. We know its Fourier series. So how is that related to the g function for the period 2 tent graph? Well, I already know how the t's have to go to pi t. So let's see what tent of pi t is. Well, it's as t is going from -1 to 1, it's just the absolute value of pi t, because pi t is going from minus pi to pi, which is pi times the absolute value of t. Okay, my g function was just absolute value of t, so g of t is 1 over pi tent of pi t. So there was a scaling going on here for the inputs in the domain, and sort of a hidden scaling going on in the range at the same time. And that's why you've got the 1 over pi as well as the pi. Okay, well, I'm now set up to use what we were talking about in the last page. To get the Fourier series for g, I just plug in pi t into the Fourier series for the period 2 function. So g of t is 1 over pi, and then I take tent of pi t, so that's pi halves minus 4 over pi, the sum over n odd of 1 over n squared cos nt. Right, so I just plugged in, cos n, need to make a little more room here. I'm substituting in pi t, so it's cosine of n pi t. So our Fourier series for G, and I can write equals because everything converges for this continuous piecewise C1 guy, is 1/2, that's 1 over pi times pi over 2, minus 4 over pi squared, the sum over n odd of 1 over n squared cosine n pi t. Okay, so let's check our work the long way, and that's just so that you can see one example worked out using the formulas for 2L periodic functions. So here we go. A naught over 2, and here we're doing it for G, so which was our period 2 tent. I'll just call it G. And G of t was absolute t from -1 to 1. So A naught over 2 is, well, we know, let's not even use the formula. We know it's the average value of G, and because this absolute value is going from 0 to 1, the average value is just 1/2. Okay, now let's do the bn's because we're dealing with an even function. So the bn's are 1 over 1, the integral from -1 to 1, absolute value of t sine n pi t dt. And we've got an even times an odd, which is an odd function, so the bn's are 0. Now let's do the an's. We get 1 over 1, integral from -1 to 1, absolute value of t, cosine n pi over 1 t dt. Integrand is even, so the an's are twice the integral from 0 to 1 of t cosine n pi t dt. And we integrate by parts. This is u, this is dv, du is dt, v is sine n pi t over n pi, an is twice, uv is t sine n pi t over n pi. We evaluate that from 0 to 1. We subtract off the integral from 0 to 1 of v du. The evaluation at the endpoints goes to 0 because sine of n pi is 0. when we look at the integral inside the parentheses, I can think of that minus as being inside, in which case the antiderivative is plus cosine n pi t. I had an n pi in the denominator. I get another one from antidifferentiating. So I get n pi squared. And I evaluate that from 0 to 1. And so I get 2 over pi squared n squared times, if n is even, then I'm evaluating cosine of an even multiple of pi, I get plus 1. If n is odd, I get minus 1. Oh, I got way ahead of myself. Let's do this right. Okay, so this is just cosine n pi at 1 minus cosine of 0, which is 1. Cosine n pi is minus 1 to the n. So what I'll get is, if n is even, I get 1 minus 1 is 0. If n is odd, the stuff inside the parentheses will be a minus 2. So we'll get a minus 4 over pi squared times 1 over n squared. Okay, and so finally, the Fourier series for G, which is the period 2-tent, is 1/2 the average value minus 4 over pi squared, the sum over n odd of 1 over n squared cosine of n pi t. And if we did everything right, after all of this work, hopefully we got the same answer as we had on the previous page by rescaling. So have a look. They're the same. Okay, so you can always do it either way. Often rescaling is the way to go. Okay, topic 2 is even and odd extension for functions defined on the interval 0, L into even or odd functions on the interval 2L, and then you extend those periodically to be 2L periodic on all of the real line. So if f is defined on the interval from 0 to L, then the way to extend it as an even function is to make f of minus t, to make f of t equal to f of minus t when t is negative. And so what you're doing is you're creating a function whose graph is symmetric with respect to the vertical axis. Okay, well, if you do that, and then, as I said, you can also consider this further extended to be 2L periodic. on all of R. Okay, so compute the Fourier series for that function. Well, a naught over 2 is the average value of this even extension on the entire interval from minus L to L, which is the same as the average value on the integral from 0 to L, which and is 1 over L integral from 0 to L of f of t dt. When you compute the cosine coefficients, your integrand is even, so you can replace the integral 1 over L times the integral from minus L to L with 2 over L times the integral from 0 to L. And when you compute the sine Fourier coefficients, you have an even times an odd, and so you get an odd function, and so the Fourier sine coefficients are all 0. So the result of extending your function to make it an even function is that you get a cosine series. But you could take the same function and hope that your screen slides. Hang on here. Oh, that's not good. Oh, geez. Technology. You could take the same function that we had before and you could define the odd extension. Oh, it did it again. Irritating. The odd extension by saying that when t is negative, the value of f will be the opposite of f at minus t, and that gives you a graph which is symmetric with respect to the origin. And then you could extend that to be 2 pi periodic piecewise continuous as well. Okay, and if you did that, then because it's an odd function, your constant term, the average value, would be 0. Your cosine terms would be 0 because you're integrating the product of an odd times an even, which is an odd function. And your sine coefficients would be 1 over L, integral from minus L to L, of f odd times sine of n pi over LT. And because product of odd times odd is even, you could replace that with 2 over L times the integral from 0 to L. And the upshot is, if you do the odd extension, you get a sine series. Okay, now what's cool, well, so as I say, we're going to use this in the upcoming applications. What's cool mathematically is if you start with a function defined from 0 to L, so say from 0 to pi, and why don't we just use f of t equals t, and and you can see geometrically that the extension is going to be the 10th function, but if f of t, so the even extension will be, well, it'll be t for 0 less than or equal to t less than or equal to pi, And when t is negative, I will take f of minus t f of minus, if t is between minus pi and 0, minus t is between 0 and pi, and so the value of f of minus t is minus t. No, no, let's be careful here. Right, I take f of the opposite, right? So t was negative, so this, yeah, so this is minus t, and minus t is the absolute value of t. Yes. Whew, I didn't do that very well. Anyway, that's why the even extension is the tent function. Let's see if I can do better with the odd extension, which we know is going to be t. So f odd of t is, well, it's t if 0 is less than or equal to t is less than or equal to pi. And it's minus f of minus t when t is negative. And this has a jump, so I don't want to put equals there. Okay, and what is minus f of minus t? Okay, so minus t is positive, so f of it is itself, and minus t is t. So just as you figured, the odd extension of t is t. Okay, I mucked that up. Anyway, what's cool is that for the even extension, you get a cosine series. For the odd extension, you get a sine series. And on the original interval, from 0 to pi, they each converge to the original function. So that's kind of super amazing. So on the original interval, both the sine and the cosine series for the even and odd extensions of t converge to the original function, which in this example was f of t equals t. Okay, so we did two main things today. We talked about Fourier series for 2L periodic functions. And we realized that they're just rescalings of Fourier series for 2 pi periodic functions. And we talked about even and odd extensions for piecewise continuous functions on the interval 0L. So that gave us 2L periodic functions, which were either even or odd. And so the even extensions gave us cosine series. And the odd extensions gave us sine series. And on the original interval from 0 to L, they each converged to the original function. Okay, that is it.